Hello, my name is Catherine Nguyen, and this is Lab 2, Motion of a Falling Object. So the main purpose of this lab is to compare the observed position of an object falling from rest to the predicted position of the object accounting for gravity and the predicted position of the object accounting for both gravity and drag. The observed position is measured using tracker, and the predicted positions are calculated using a computational model on GlowScript. For this lab, the object is a crumpled piece of paper. Just to give a brief preview of the results, the predicted computational model that takes into account gravity and drag will be more similar to the observed model than the predicted computational model that only takes into account gravity, which we will explore in the rest of this presentation. So the main principle to consider is Newton's second law, which states that the acceleration of an object is proportional to the force applied to the object. Additionally, Newton's second law also gives us that the rate of change of the momentum of an object is proportional to the net force applied on it. We use this understanding of Newton's second law to derive the velocity update formula and the position update formula. We can also use it to find the sum of the forces acting on an object as it interacts with its surroundings. One such force is the weight force, which is the downward force acting on the mass due to the acceleration of gravity, which can be seen here as Fg. Another important force is the drag force, which acts in the opposite direction to the motion of the mass, which is denoted here as Fd. So I first started this experiment by recording a video of a crumpled piece of paper being dropped from rest from approximately 1 meter off the ground. To obtain my observed data, I uploaded the video onto Tracker and tracked the motion of the object in equal time intervals to create a position versus time graph. Next, I created the computational models by editing the starter code on GlowScript. Lastly, I uploaded the data from Tracker and GlowScript onto Google Sheets to compare the data of position over time. Here's a video on Tracker of the crumpled piece of paper being dropped from rest. The little red dots are inputs of the positions at a certain time. Over on the side is the graph that the program generates of the position versus time graph. As you can see, there is a slight curve in the slope. One important thing to mention is that the crumpled paper is the system, while everything other than the crumpled paper is its surroundings. So with the data we collected, we can see that the initial position is 1.036 meters in the y direction, and the initial velocity is 0 in the x, y, and z direction because it is starting from rest. The total time for the crumpled paper to drop is 0.502 seconds. So this is the computational model accounting for gravity only. I first started by changing the mass of the object to the mass of a single sheet of paper, which is 0.0045 kilograms. I then inputted the initial position and velocity vectors obtained by Tracker as my initial conditions. I changed the delta t to 0.033 because each data point was taken every 0.033 seconds. Gravity should be 9.8 meters per second squared, and j hat should be 1 in the y direction because we are observing the motion in the y direction. I changed Fnet to be the formula of the weight force, which is negative times the mass of the object times acceleration due to gravity times j hat. I then inputted the position and velocity update formula into the code. And finally, I was able to run the code and collect the data. On this graph, the observed position is in blue and the predicted position is in red. As you can see, the observed position is a bit higher than the predicted position, showing that the paper fell slower than what was predicted. Now let's look at the computational model accounting for gravity and drag. Much of what I changed before stayed the same. One of the things I changed was b, which I changed to 0.005 after playing with the code for a bit to see what aligns the best. This value goes into the drag force formula over here, which I added to the net force. This should cause the code to account for both gravity and drag when calculating the position of the object over time. So on this graph, the predicted position accounting for both gravity and drag is in yellow. As you can see, this new predicted position is a lot more similar to the observed position in blue than the predicted position only accounting for gravity, which is in red. This is because in reality, as the object falls, there is a drag force acting on it due to air particles pushing against it as it moves. So for some possible errors. One possible error may have been an error in the tracker. When I was tracking the crumpled paper, I may have misplaced the tracking inputs on the object. Additionally, there may have been scaling errors. The program may have thought that I dropped the object higher or lower than what I actually did. Another possible error is human error. It is possible that a small force may have been applied to the object as I released it from rest. So for some further questions, what does it mean for there to be terminal velocity? Well, when an object has reached a state where it is experiencing terminal velocity, then the net force equals 0, meaning the weight and drag force are balanced. When you compare these two models, you can see that the model accounting for both gravity and drag down here begins to steady out right at the end. This shows its state of getting closer and closer to terminal velocity where the velocity is constant. So what if the object was thrown downward? Well, this wouldn't affect the terminal velocity. It would be the same even if there was an initial force in the negative y direction. That is the end of my presentation. Thank you for listening.